Let's take a look at using limit laws to help us find limits of functions. So our first example here is the limit as x approaches 2 of x squared minus 4 over the quantity x minus 2. So using the quotient limit law, we can think of this as the limit as x approaches 2 of x squared minus 4 over the limit as x approaches 2 of the quantity x minus 2. Then using the difference law, we could think of this as the limit as x approaches 2 of x squared minus the limit as x approaches 2 of 4 over the limit as x approaches 2 of x minus the limit as x approaches 2 of 2. Now, in the numerator, this first term, the limit as x approaches 2 of x squared, well, as x approaches 2, x squared will approach 4, minus. Now, looking at our second term, the limit as x approaches 2 of 4, notice that the value of x does not affect the quantity here. That 4 remains 4. It is not affected by x approaching 2. So we would have 4 as our second term. Moving to our denominator, we have the limit as x approaches 2 of x. Well, as x approaches 2, my function x will also approach 2, minus, and then my second term in my denominator, limit as x approaches 2 of 2. Well, the fact that x is approaching 2 will not affect the value of that 2. So we will have 2 minus 2 in our denominator. So it ends up in giving us a situation where we have 0 over 0, which is referred to as indeterminate. Okay, we can't divide by 0, and the fact that the numerator is a 0 creates issues. So what we're going to do is we're going to go back and look at our function and see if there is a way for us to simplify the function, and through that simplifying process, create a limit that we can actually evaluate. So let's notice that we could factor our numerator. So we would have a limit as x approaches 2. And our numerator factors to x plus 2, x minus 2 over x minus 2. Now notice that we have a common factor of x minus 2. And this creates now a limit as x approaches 2 of x plus 2, which would give us x approaches 2, then x plus 2 approaches 4. So our limit here is 4. Now, let's take just a moment and think about what the implications of this simplification we just did. So our function originally was x squared minus 4 over x minus 2. And we noted that this is x plus 2 times x minus 2 over the quantity x minus 2. And in essence, we divided out this common factor of x minus 2, leaving us with x plus 2. Now, we have to be careful. In algebra, we talk about this idea that x squared minus 4 over x minus 2 has the same function values as x plus 2, provided that x does not equal 2. because we removed information here in our original function. This denominator of x minus 2 reminded us that we could not evaluate the function at 2. We would have 2 minus 2 in the denominator, and division by 0 is undefined. When we simplify that and we end up with this x plus 2, we've removed that information. So we have to include this caveat of x cannot equal 2 to produce the same function values as the original function. Now, with a limit, we're not interested necessarily on what happens at 2. We want to know what happens close to 2. So the fact that we're using a function that's defined everywhere but at x equals 2 as a way of approximating the behavior of our original function is okay, because when we're looking at a limit, we never take into account what happens to the function exactly at 2. So we're going to look at a couple more examples of using factoring to help with finding the value of a limit. So in our next example here, if we were to take the limit of the numerator, so limit x approaches negative 4 of 0.5x squared minus 3x over the limit as x approaches negative 4 of x, let's see what happens. Well, in the denominator, that's fairly straightforward. As x approaches negative 4, then my function x will approach negative 4 as well. And then if I look at my numerator here, as x approaches negative 4, this 0.5x squared will approach 0.5 negative 4 squared, and this minus 3x will approach minus 3 times negative 4. Now, simplifying our numerator, negative 4 squared is 16 times a half is 8. Minus 3 times negative 4 is plus 12, divided by negative 4. So we would get 20 over negative 4 equals negative 5. So you'll notice that we didn't run into the situation of division by 0 in this particular example, and that we were able to use the limit laws to arrive at our final limit. Now, let's go ahead and look at another example. Now, let's take a look at this limit as h approaches 0 of the quantity 2 plus h squared minus 4 divided by h. If I go ahead and try to use the limit laws without any manipulation, we'd have 2 plus limit as h approaches 0 of 2 plus h squared minus 4 over the limit as h approaches 0 of h. And then taking the limit in our numerator as h approaches 0, 2 plus h will approach 2 plus 0 squared minus 4. And my limit in my denominator as h approaches 0, then my function h also approaches 0. So in my numerator, I end up with 0 over 0. So again, this indeterminate form, which cues me in to thinking about trying to use algebra to modify the function, simplify the function to create something, a form that can produce a finite limit. So as we work through this problem, we're going to pay attention to notation and what that notation is conveying about what the concept is that we're trying to investigate. So when I look at this notation here, the fact that this says limit as h approaches 0 is telling me that the question under consideration is, how does my function here behave as h gets close to 0? We don't care what happens to the function at 0, but we want to know how the function behaves as we get closer and closer and closer to 0. So it's important that I continue to use this notation because that continues to indicate that we're still thinking about the function behavior and that we haven't yet answered the question about how this function behaves. So we'll have the limit as h approaches 0. We'll go ahead and multiply out that numerator. So 2 plus h quantity squared is 4 plus 4h plus h squared minus 4. That's our numerator. And h is our denominator. So now let's see what we can do with our numerator. We see that we have a positive 4 and a negative 4. And those two terms sum to 0. So we're still thinking about how this function behaves. So we keep writing the limit notation. And now as we continue on, let's see, my denominator's h. In my two remaining terms, my 4h plus h squared, I have a common factor of h. So I will factor that out, and that leaves me with 4 plus h. And now I see that I have a common factor in my numerator and denominator of h, so I can divide those out, leaving me with the question of how does the function 4 plus h behave as h approaches 0? Well, that would behave as 4 plus 0. Now, notice I'm not writing that limit notation anymore because I'm now ready to answer the question. I now have the function in a form where I can answer the question about how it behaves. That's 4 plus 0, which would tell me that this limit is 4. Let's look at one more. We've got the limit as x approaches 3 of the quantity 4x minus 12 over the quantity x squared plus 2x minus 15. Using that quotient rule, if I take the limit of the numerator, 4x minus 12, over the limit of the denominator, limit as x approaches 3 of x squared plus 2x minus 15. Let's see, what happens to 4x minus 12 as x approaches 3? Well, 4x minus 12 would approach 4 times 3 minus 12. And in my denominator, what happens to x squared plus 2x minus 15 as x approaches 3? Well, that would approach 3 squared plus 2 times 3 minus 15. And if I simplify my numerator, I get a 0. And 9 plus 6 is 15, minus 15 is 0. So again, this indeterminate form. So I need to see if I can rewrite the function in a more simplified form that will allow me to find the limit. This in a simplified form so that we can see how this original function, 4x minus 12 over x squared plus 2x minus 15, how it behaves as x approaches 3. So we'll have the limit as x approaches 3 of, 4 times x minus 3 over x plus 5 over x minus 3. And at this point, we can see that we do have a common factor. We can simplify that, divide them out, and they, in essence, become a 1. So we're not quite ready to answer the question about how this function behaves. So limit as x approaches 3, 4 over x plus 5. Now looking at that, it looks in fairly simplified form. It looks like I could now answer the question about how my original function behaves as x approaches 3. As x approaches 3, the numerator doesn't change because it's a constant. As x approaches 3, my denominator will approach 3 plus 5. So that would give me 4/8 or 1/2. So as x approaches 3, as x gets closer and closer to 3, this function 4x minus 12 over x squared plus 2x minus 15 gets closer and closer to 1/2. I hope this helps.